All right, so this chapter was carboxylic acid derivatives. Like I said, we kind of lump all these molecules together into the same category, and that's because that's helpful in understanding the reactions of these carboxylic acid derivatives. All right, so now we're going to talk about conversions of our carboxylic acid derivatives. What we're going to see is that we can convert from one carboxylic acid derivative into another, okay? But what we're going to need to do is we're going to take all of these carboxylic acid derivatives and we're going to rank them. We're going to rank them from the most reactive to the least reactive, okay? So we're just going to make this big list here. I'm going to start with the most reactive carboxylic acid derivative at the top. All right, and that most reactive carboxylic acid derivative is when that carbonyl carbon is bound to that halogen. We call these our acyl halides. All right, what you're going to see is I'm going to make this list, and I'm kind of going to stagger them a little bit. I would trust me on that. It's going to be helpful with how we lay out our notes here in a second. All right, I'm going to throw a few extra at us that we're going to need to know as well. All right, this one is also one that you'll see in your homework. This is when we have an oxygen bound here, almost like an ester, but it's sandwiched in between two carbonyl groups. These are also very reactive carboxylic acid derivatives. They're very good starting points for synthesis reactions. We called these acid anhydrides. Okay. The other one is going to be a new one. This is like an ester, but if instead of having an oxygen, I had a sulfur, this is what we call a thioester. All right, our thioesters are followed by our normal old esters. All right, and in terms of our reactivity, these normal old esters are actually tied with another one of our carboxylic acid derivatives. So I'm going to put directly next to it the namesake of our functional group category here, the actual carboxylic acid itself. All right, and then the last one on our list here is if we had a nitrogen in this position, our amides. They are considered our least reactive carboxylic acid derivative. Okay. Cool. So why did we make this little ranking system here of most reactive to least reactive? All right. I'll give you a second to finish copying this down here, drawing our molecules. All right. But the punchline here is we're going to learn how you can convert something that's more reactive into something that's less reactive, right? We can always go from something more reactive to something less reactive. We can't really go the other direction. There are a few special cases that we'll talk about, All right, but for the most part, converting something like an acyl chloride at the very top to any one of these other ones is really easy to do, okay? But if we start with an ester, we can only really convert that to a carboxylic acid or an amide, right? So we can always go from more reactive to less reactive, all right? And that's our conversions of carboxylic acid derivatives that we're talking about, okay? So again, what we're going to see is that we can convert from more to less reactive carboxylic acid derivatives. Okay, that's going to be kind of the punchline of this series of reactions that we learn. Okay, so a good question would be why? Like, why can we go one direction but not the other here? All right, so let's just grab one of these more reactive carboxylic acid derivatives. And we're going to say we're going to convert this thing into one of our less reactive carboxylic acid derivatives. We'll go for an ester. Okay, and again, we can go in this forward direction, but we can't go in the reverse direction. All right, and again, the question is why? Okay, well, what bond am I going to have to break on my reactant side here in order to make my new ester? What bond gets broken over here? What bond's over here that's not over there? The carbonyl carbon and the chlorine, right? So in order for this reaction to occur, we're going to have to kick off that chloride ion. Right? Why are these acyl halides so reactive? Because this leaving group here is super duper stable all by itself. Chlorine is more than happy to have a negative charge associated with it. If we try to go the other direction, I guess I did this kind of backwards here. If we tried to go the other direction, then we'd have to break this bond here, and we'd kick off this negatively charged oxygen. Oxygen is not as stable with that negative charge. All right, so the bottom line is, what does our ranking here represent of most to least reactive? These are ranked from most to least reactive because that group that you're kicking off is a better leaving group. All right, so why? Because you remove the better leaving group. All right, remember we've heard this term before. Why is it a leaving group? Because it leaves. It gets kicked off when this reaction occurs. Okay, so to be clear, if I'm going to go up here and sort of identify what my leaving groups are, let's just use it in blue here. In our acyl halide, again, we're going to break this bond right here. All right, the acid anhydride, and let me be good with my lone pairs, getting lazy at the end of the semester. The acid anhydride is the one I kind of want to point out the most because it's a little bit confusing because it's a big molecule. But it's actually this whole thing right here that's going to play the role of the leaving group in these reactions, right? You're going to kick off that whole thing, which is going to be this negatively charged oxygen. But since it's right next door to that other carbonyl group, it gets resonance stabilized, so it's that much more stable than a regular old negatively charged oxygen. Sulfur is a fairly decent leaving group, better than oxygen, but not as good as a halogen. Because it's so large, it's not as angry with that negative charge. Our esters and our carboxylic acids are tied, right? And why is that? Because their leaving groups have the same stability. They're both oxygens with negative charges. Okay, and then an amide, you would have to kick off this nitrogen here, and nitrogen is absolutely furious having a negative charge, all right? Very unstable to have one of those negatively charged nitrogens. Okay? So we can go from something more reactive to something less reactive by kicking off these leaving groups here. And again, our ranking is just in terms of how stable those leaving groups are once you kick them off. Cool. All right. So how would we do it here? How would we, for example, go from our acyl chlorides, this is why we wanted to stagger them here. We're going to make this cheat sheet here, to each of these different compounds. Right? So let's just kind of take a zoomed in view. Let's do our previous example here. Our acyl chloride to our ester. How would we do it? Said we can't go in this direction. How do we go in that forward direction? All right, well, what am I trying to add here? This thing, right? This is what I need to add to our molecule. Okay? Cool. So I can't just say copy, paste just as is, because all of a sudden I've completely violated this oxygen's octet rule. All right? So what we could do is instead, we're just going to give it a hydrogen. Right? We're going to use this alcohol here, add it to our acyl halide, and what we'll get is this substitution reaction where we kick off that chloride and we replace it with that nucleophile, our alcohol. Let me clean this up. This is going to bother me. All right, so notice how this exactly matches what I'm trying to substitute on there, and then I just added a hydrogen so I don't violate the octet rule of that molecule. Okay, let's try to do another one. All right, I want everybody to take a second. Tell me how we would turn an acyl halide into instead a carboxylic acid. All right, what nucleophile would we need to use to do it? All right, so I'm going to pick up this thing right here. OH. And what am I going to do to it? add another hydrogen. And this is a really weird way of writing the molecular formula for what molecule?
Water.
For water. Right? So by adding water, I can turn that acyl halide into a carboxylic acid. Okay? So if we're going to fill in our little cheat sheet here, how do we go from A to B? Again, we just need to look at what we're trying to replace. That's our nucleophile, and we're going to add a hydrogen to it to make it neutral. Okay? Now, you may have asked, well, why couldn't we have just left that hydrogen off? I could have said OH minus, and this totally works as well. I forgot a lone pair, so my octet rules, there we go. This works, all right, but why the heck are you going to spend money buying hydroxide and putting it into solution where you could go to the tap and just add straight up neutral water? So in just about every case, a nucleophile is practically way more expensive if it's deprotonated than it is protonated, right? So an alcohol is way cheaper than a deprotonated alcohol, an alkoxide ion. So these are all just like practical reasons. It's not like it wouldn't work, but why? You're going overboard, right? So again, what we're going to say is we're going to use the neutral form of our nucleophile in each of these reactions here. Okay, there is going to be one exception, and that is this very first step here, going from an alkyl halide to an acid anhydride. The protonated form of this here would be a carboxylic acid, and it's just a really crap nucleophile. So in this case here, we would have to use that carboxylate ion, that deprotonated carboxylic acid. All right, but this is kind of the only special case. All of these other ones, we can just use the protonated form of that nucleophile. All right, so let's actually just take these one by one. If we wanted to turn an acyl halide into a thioester, we're going to use this thing right here. Does anybody remember what our functional group is? SH. Thiol. Awesome. So we would have to use a thiol. If I'm going to convert an acyl halide into an ester, I would use something with the formula OH. And what do we call those? Alcohols. A carboxylic acid would be water. All right, and then if I wanted to make an amide, I would use these nitrogen-containing functional groups. In this case, I could use ammonia because it's the smallest one. All right, there might be a carbon coming off of this amide. We'll do an example to see that. Cool? All right, so then what if I wanted to turn my acid anhydride into a thioester? What am I going to use? Same thing. You're just going to use that thiol, right? Because we can always go from something more reactive to something less reactive. All right, so this table might get a little bit redundant here. But exactly, you're just going to be able to use the same thing because we can always go more reactive to less reactive. All right, so again, if I wanted to convert that acid anhydride into an ester, I would just use an alcohol. To a carboxylic acid, I would use water. And to an amide, I would use an amine. All right. Same thing with our thioesters, nothing special. All right, there is going to be a little bit, I can't make it that easy. There is going to be a little bit of a hang up when we get to this very last step. We'll talk about that. All right, but a thioester you can convert to an ester, again, just using an alcohol. Convert it to a carboxylic acid just using water, or to an amide rather, using an amine. Cool? All right. So the last sort of tier here. First of all, we're going to talk specifically about going between carboxylic acids and esters. That's going to be kind of its own separate category. But when we get to this last tier here, we can go from a ester to a to an amide, like kind of nothing special, exactly using the logic before NH3. Okay? But we cannot go from a carboxylic acid to an amide. All right? We got a problem here. All right? So even though carboxylic acids are more reactive and amides are less reactive, we got a problem trying to convert between these two. Okay? So let's see why that would be. All right, let's take our carboxylic acid. And let's do the same game that we would if we were, talking about any other more reactive functional group. We're going to add in some amine. All right. Let's just say carboxylic acids and amines. All right, and I kind of already gave you the punchline here. They do not produce amides. All right, but why? Why would that be? Okay, so in these reactions, we're sort of dependent on that electrophilic carbonyl carbon. And that's what ends up being substituted in these reactions, right? That's why we add in that nucleophile. But both of these ends, so we have an electrophile here, we have our nucleophile here, all right? So why don't we have this nucleophilic substitution reaction like we do in every other case? Because these are not just nucleophiles and electrophiles. Carboxylic acids can also play the role of what? It's built into the name of an acid, right? And amines are great bases. And so the problem here is that we don't get this nucleophilic substitution reaction instead, immediately, very quickly, we have instead an acid-base reaction where we have our acid donate that proton, leaving us with that negatively charged oxygen. And our base accepts that proton. So now I'm going to draw its formula with an extra hydrogen. And since it accepted that positively charged hydrogen ion, it has a positive charge. All right, so instead of having a nucleophilic substitution reaction, we get an acid-base reaction instead. All right, and at this point, these molecules are stuck. Nitrogen no longer has a lone pair to play the role of a nucleophile. This carboxylate ion's got a bunch of negative charge, so it's no longer a good electrophile, right? So we just don't have our same reaction that we had before. We just have this very quick acid-base reaction, and then we're kind of stuck there, okay? Cool. So then the last one I said that we're going to talk about, we're going to kind of do a deep dive on, I guess second to last one, is this step right here, right? These two we said were tied with one another, okay? And because of that, we can actually freely convert between esters and carboxylic acids. This is what we call a very dynamic equilibrium, where the free energy change is not very much at all, right? So at equilibrium, they're both sort of in appreciable concentrations. This is what we call a Fischer esterification reaction. And I think the name is a little bit misleading because, yes, you can convert a carboxylic acid to an ester, but you can also go the other direction as well, right? So in our Fischer esterification reactions, this allows us to convert from carboxylic acid to an ester, or the other direction. All right, so let's look here. If I have my carboxylic acid, and I wanted to create instead an ester, what would be the functional group of the nucleophile that I would add in there? OH, right? And what do we call those? Alcohols. All right, so if I want to go in this direction here, I'm just going to add an alcohol. All right, but now let's look in the reverse direction here. If I started with my ester, what would I add in order to get a carboxylic acid? Starting here, going here, what did we add to make carboxylic acids? H2O. Okay? All right, again, this is what we call a dynamic equilibrium. One side of this reaction isn't super favored compared to the other side. All right, so we take advantage of this and using what's called Le Chatelier's principle to tune this reaction to go whatever direction that we want, right? So let's say that I really wanted to make an ester. I would start with my carboxylic acid, and then I would just dump in a boatload of alcohol. And due to Le Chatelier's principle, that would have the effect of pushing that equilibrium in favor of our product side. Right? Or let's say I wanted to go the other way. I would just start with my ester and I would put in a huge excess of water. And that would have the effect of shifting the equilibrium in this direction, right? So this is like this highly tunable reaction where just by adjusting the concentrations, we can shift things in one direction or the other. We can't do that if a reaction really favorably favors one side over the other. Like the combustion reactions, for example. You're never going to uncombust gasoline. It's gone, right? That is an equilibrium that favors that product side to the nth degree, all right? But this one here is a very balanced equilibrium. So just by adjusting the concentrations of our reactants, we can shift it in one direction or the other, all right? So dynamic equilibrium. We're just going to make note what that means. We can shift the reaction in favor of the products by adding an excess of alcohol. Or we can make it go the other direction. We can shift the reaction in favor of our reactants. By adding excess water. Okay, and to be clear, according to Le Chatelier's principle, you could also shift this by adding, let's say, an excess of ester. That would help push this reaction in this direction as well. But again, thinking practically about what's going to be our cheaper reagent here, it's way easier to have an excess of water than it is an excess of ester, right? Also practically at the end, if you want to separate stuff out, all right? But anyways, yes, so this is what we call a dynamic equilibrium. They are equal on our little reactivity series. We can shift freely, we can convert freely from one to the other. All right? The only thing that we're going to note about our Fischer esterification is in order to do this conversion on a time scale that's not going to take 1,000,000 years, we put a catalyst in there, and that is just a simple acid catalyst here. I'm going to put this H3O to indicate that we have this acid catalyst. Okay? Cool. So let's say that I had a carboxylic acid and I really wanted to convert it to an amide. For the reasons that we just discussed previously, you're not going to be able to just add in your ammonia, add in your amine. Instead, you could go add add alcohol first to create an ester, and then convert that into amine. So you'd have to do it a little bit of a roundabout way. You'd have to add an extra step in there. But of course, we could go from a carboxylic acid to an amide. We would just have to go through that ester intermediate. All right, now, we did say that we had one way of going in the reverse direction here, right? Converting a less reactive to a more reactive carboxylic acid derivative. And the way that we're going to do that is by using something kind of fancy, basically. All right, we can convert a carboxylic acid into an acyl halide. Even though our carboxylic acids are less reactive and our acyl halides are more reactive, we got a way to do it here. Okay, so we take our carboxylic acid, and we want to make an acyl halide. Specifically, we're going to be able to make acyl chlorides. All right, and I am teaching too many organic chemistry courses at this point, so honestly, I can't remember if we've seen this one before or not, but this is a reagent that we may or may not have seen before, SOCl2. What's called thianyl. No, we have not, because we didn't do substitution of alcohols, which is the problem I put on that I wasn't supposed to. Okay, anyways, thianyl, I don't know, chloride. SOCl2. And that's our one way of sort of going back to the starting point. And this is super helpful because our acyl chlorides are the most reactive one, right? So we can sort of go back to the beginning and then, go from there. That's a great starting point for any sort of synthesis reaction. Okay, cool. Let's practice this here. I'm going to put down some reactions, and you're going to tell me what nucleophiles we need to be able to do these conversions. Okay? Cool. All right, so let's do this first one here. How are we going to do this? I'm going to look at what it is that needs to be attached. All right, I'm going to note that this ester group here has 1, 2, 3 carbons. So I'm going to need to use a 3-carbon alcohol or 1-propanol in order to do it. All right, again, what I boxed in orange there matches my nucleophile.
So it would be H3O plus.
Say it again?
So it would be H3O plus.
No, so in this case, you're starting with something more reactive and going to something less reactive. So you just need to add the nucleophile that matches what you're trying. That was very specifically for esters to carboxylic acid since they're on the same level of reactivity. That's the only one you need that acid catalyst for. Okay, truthfully, it would work if you added acid, but again, why? Why are you spending the money to do it? Okay, so same thing. I'm just going to match my nucleophile here. So now I'm going to have to use a thiol, and I just got to make sure that it's got the same number of carbons and that my branch point is in the correct position. Okay, and again, just note that my nucleophile there matches, or rather my new group that I've added there matches my nucleophile. I've just added that hydrogen to make it neutral and make sure sulfur's octet is not broken. Okay, now for this one, can I do this one in one step here? No, what's the problem? We're trying to go from something less reactive to something more reactive. Okay, but now let's say, so fine, we can't do it in one step, all right? But the boss is on our ass. We need to create this acid anhydride real bad, all right? So how are we going to do it? We can use 2 steps if we need to. What are we going to have to do first? The SOCl2, right? So we can get away with it if first we convert this thing to an acyl chloride. And then what would we need to do for this next step here? All right, remember this was our one exception where we would have to use that negatively charged version of our nucleophile. We can't get away with our neutral carboxylic acid. We would have to use this carboxylate ion that has that negative charge. Okay, so we couldn't do it in one step, but we could do it in these 2 steps here. All right, again, using that fancy thionyl chloride reagent. Okay, and I would just note, this is our only negatively charged nucleophile that we got to use in this section. Okay? Cool. So our carboxylic acid derivative conversions here. We took all these carboxylic acid derivatives and we ranked them from most reactive to least reactive. And really what we were doing is ranking them from best leaving group to worst leaving group. Okay? And we can freely convert from something more reactive to something less reactive by adding the nucleophile that matches what it is we're trying to substitute. We had some, I guess asterisks that we had to keep in mind here, right? We couldn't make this conversion from a carboxylic acid to an amide. Instead, we have that acid-base reaction that occurs. And we have esters and carboxylic acids that are on the same level of reactivity. We can actually freely convert between the 2 of them. We just need to have that acid catalyst in there as well. Okay? And then lastly, we do have one way of going back up to something more reactive, and that's starting with our carboxylic acid, and we can create an acyl halide using that thionyl chloride reagent. Cool. All right, hardest part of the course here. We're done. Congratulations. No more content. Fantastic. All right, I'll let you know what the results of the survey are here in a minute when I check things out, and I'll let you know what we're doing Tuesday of next week. But this closes out all the new material that we have. You just got to make sure to study. These chapters were a little bit shorter, right? So we have more chapters. We spent about a week on each of them. There's a little bit more functional groups, a little bit more nomenclature, all that sort of stuff. All right, but good luck finishing out the rest of the semester, and I'll see you next week. The last one? This one? Yes. That very last step? Yeah. All right, have a good one.